Hey, what's up everyone? I'm gonna be starting a series of videos on physics units for A and AS level, and I'm thinking of doing it using the learning objectives set by Cambridge University, and hopefully you guys will find it helpful and make physics easier for you. So let's begin. The first unit is about physical quantities and units. Now, the contents of this unit is mainly physical quantities, and we're going to be talking about SI units, the Avogadro's constant, and scalars and vectors. So in this video, we're gonna be mainly focusing on the learning outcomes that Cambridge wants his students to know. So part A is show an understanding that all physical quantities consist of a numerical magnitude and a unit. Now this part is quite self-explanatory. I'm just gonna briefly write what it means and we're gonna see some examples of it. Now a physical quantity essentially means that it is a quantity which can be measured using physical means, that is instrument, such as length can be measured using a ruler, temperature using a thermometer. And when we're talking about physical quantity, obviously it has a magnitude and I made a mistake, I just corrected it, and a unit. So now let's look at some examples of physical quantities. So here I just written some physical quantities. We have length, we have temperature, we have height. Now let's move on to part B. Part B of the learning outcome says that we have to recall SI base quantities and the units. I'm just gonna draw a table quickly showing the SI base units, the base quantities that you need to know, and their corresponding units. Okay, so here we have it. We have mass, which is measured in kilograms. We have length, SI unit being meters. Time measured in seconds. Current measured in ampere. Temperature measured in Kelvin, and amount of substance measured in mole. Part C. It says express derived units as products or quotients of the SI base units. So we're gonna be doing this one by one, and I'm gonna be drawing a table. So the first derived quantities is area, which is the easiest one, and we all know that area is equal to length to the square, or any the dimension to the square. And the unit for length is meter, so it is meter times meter, which gives us meter square. Likewise for volume, it is L cube and it is meter cube. Now for density, density is another kind of derived quantity, in which for this one the formula is density equals mass divided by volume. And for mass, the unit is kilogram and the unit for volume is meter cube. Now in the exponential form, we can just put the meter cube on the numerator side, and this becomes kg meter minus 3. Now let's move on to velocity. Now velocity is change in distance, so let me just write it, change in displacement divided by time. Displacement, the unit is meter, and time, the unit is second. So exponential form, this is meters per second. Now let's talk about acceleration. Now acceleration is change in velocity divided by time. Already we know that velocity is meter per second, and we divide this by time, and now we have m, and we put this s on the numerator side, it becomes s minus 1. So minus 1 minus 1, this becomes s minus 2. So the unit of acceleration is meter per second square. Momentum, how it is calculated is just mass times the velocity at which the body is moving. and for mass it's kilogram, and velocity is meter per second. So the units for momentum is kg meter per second. Okay, let's now move a bit further and let's take a further look at the derived quantities. The first one we're gonna be seeing is force. Now the definition of force in physics is force is defined as the rate of change of momentum. So it is the change in momentum divided by time. And the special name given for force is, the unit is Newton. And the symbol for Newton is N capital. Now let's go and try to derive the unit for force. Now we know that momentum has the unit, as we have seen here, is kilogram meter per second. So we're just gonna put it here, kilogram meter per second. Now this is divided by time, so it is second on the denominator. Rearranging this, we get kilogram meter per second square. So this is the unit for force. Now let's look at pressure. Now pressure is defined as the force acting per unit area. So it is force divided by area. Force, we just found out the units, so we're just gonna have to replace it here. Now force, the special name given for the units of pressure is Pascal, and the symbol is P capital and A. Deriving the units, we said we're just gonna put the units for force here. So this is kilogram meter per second square divided by the area, which is meter square. And rearranging this, we get kg meter minus 1 and per second square. Now let's look at energy. By definition, energy is force multiplied by the distance traveled by the point of application of the force in the direction of the force. So this is force times distance, and the special name given for the unit is joule, capital J. Force, we're just gonna put in the units for force, and distance is meter. So overall this gives kg meter square per second square. Now let's move on to power. Now power is defined as the rate of doing work. So it is, work is essentially energy divided by time, and the special name for the units is watts, capital W. So we have kg meter square per second square divided by seconds, and rearranging it gives kilogram meter square per second cubed. Okay, so this is about part C. Now let's move on to part D, which says use SI based units to check homogeneity of physical equations. Now homogeneity basically involves checking the validity of an equation by verifying if the units and dimensions on both sides of the equation are equivalent. Otherwise, the equation is said to be not physically correct. For example, let's take Einstein's famous equation E equals mc squared, and let's see if it is physically correct. So we have energy equals mass times the square of the speed of light. Let's see the units for energy. Now we know that energy is calculated by force times distance, and this should be equal to mass times c squared. Now force from Newton's second law, that force equals mass times acceleration. So we're just going to be using this here. So force equals mass times acceleration. times this distance and equals mc square. Now let's use the units. For the left hand side we have mass, and the units for mass is kilogram. Acceleration is meter per second square, and distance is meters, and this should be equal to the units on this side, which is kilogram, times meter square times second minus 2. So this is basically meter per second squared, so that's meter square and per second square. Let's simplify this part. This gives me kilogram meter square per second square, and this is equal to this one. Therefore, we note that units on the left hand side is equivalent to the units on the right hand side, and hence we can conclude that this equation is physically correct. So this is other way of saying it is that this equation is homogeneous. So this basically is what homogeneity is about. Part E, so it says show an understanding and use the conventions for labeling graph axes and table columns. I'm just gonna draw some graphs and show that how we are supposed to label the axes. So what's important to note here is when labeling the graphs, on the y-axis we have the dependent variable, and on the x-axis we have the independent variable. And it is important to write what is the physical quantity that we are measuring, and the units, they can be put in brackets like I have put here. The first example is showing velocity against time, and the second example is momentum, and see the way I have put the units in brackets, like it is clear, and we know exactly what we are trying to measure, and we know the units against time, and this one acceleration against time. Now let's move on to part F, which is the use of prefixes and symbols to indicate decimal submultiples or multiples of both base and derived quantities. So the prefixes are pico, nano, micro, milli, centi, deci, kilo, mega, giga, and tera, and the corresponding symbol have been given. For pico it's small p, nano is small n, and for micro it's mu, and so on. And note that mega, giga, and tera are capital letters. Now looking at the multiplying factor. So for pico it's 10 to the minus 12, for nano it's 10 to the minus 9, micro 10 to the minus 6, and so on. And we have mega, which is 10 to the 6, giga, which is 10 to the power of 9, and we have tera, which is 10 to the power of 12. Okay, let's keep moving. So now we go on to part G, which says make reasonable estimates of physical quantities included within the syllabus, of course. And it is important to note that it is estimates of common things in everyday life, and it is something which physics students should be familiar with. When we're making an estimate, it is reasonable to give the figure to one or two significant figures, as it is an estimate and hence there is some lack of precision. I'm just gonna put some common examples. Let's take the mass of 3 cans of Coke. Now how are we going to estimate this? Now we can assume that 1 can approximately is 330 ml. So 3 cans, this gives us 3 times 330, which is approximately, which is 990 ml. Now for the cans, we can suppose that the main constituent is water. and we can say that water has a density of approximately 1 gram per milliliter. So this gives me, converted into grams, approximately 990 grams. So I can say that at the end of the day, 3 cans of Coke weighs about 1 kilogram. Now the second example I'm gonna take is the mass of a medium-sized car. We can say that we know that a car is approximately 1 or 2 tons. So it is reasonable to say that the mass lies within 1000 to 2000 kilograms. Now for the mass of an apple, it is quite reasonable to estimate that an apple weighs approximately 100 grams. Now this keeps on going, these estimates, and we just have to be like imagine what is the range that it might actually lie. And it is important that we get used to everyday things like taking measurements of small things and all that. Say for example, I have to measure the thickness of a page. Now how I'm gonna do that, I'm not going to use a micrometer or whatsoever. I'm just gonna, let's say, take a bunch of 10 pages and put my ruler on it. So it approximately averages to 1 millimeter. So I divide it by 10. So this gives me an approximate value of the thickness of a page being 0.1 millimeter. Moving to part H, which says show an understanding that the Avogadro constant is the number of atoms in 12 grams of carbon-12. Okay, so I'll just briefly give the value of the Avogadro's constant and a brief description of what it is. So the Avogadro's constant has a value of approximately 6.02 times 10 to the power of 23 particles per mole, and it is the number of particles contained in exactly 12 grams of carbon-12, which is equivalent to 1 mole of a substance. In part I, we're gonna talk about scalar and vector quantities. Let's start by defining what is a scalar quantity. So it is one which has a magnitude but no direction. An example of scalar quantities are distance, speed, mass, time, temperature, energy, pressure, power, electric charge, and so on. And a vector quantity is one which has a magnitude and a direction. Examples of vector quantity are displacement, velocity, moments, momentum, force, electric field strength, and so on. In part J of the learning outcome, we're gonna be talking about how we add and subtract coplanar vectors. Let's take this arrow to be vector A and this second arrow to be vector B. Now let's add both of these vectors. Now when adding the vectors, it is important that the vector begins with the tail and the direction is shown by the way the arrow is pointing, and the other vector, it is a tail of that vector which joins the head of the first vector, as I'm gonna show here. Now for the resultant vector, we just draw a line here and the head joining here, and we usually use a double arrow to indicate that it is a resultant vector. So this is vector A plus vector B. Okay, so now let's talk about subtraction of vectors, and I'm gonna do A minus B. So when I'm doing A minus B, it's actually doing A plus minus B. So this minus B shows that the direction of the vector is reversed. So if I have a vector b pointing in this direction, the vector minus b will be pointing in this direction. So the vector b resembles something like this, and the resultant vector a minus b, we just have to join this part to this part. There we go, the vector a minus b and the vector a plus b. Now note that the vector begins from the tail of the first vector a and ends with the head of the vector b. It is the same case here, begins with the tail and ends with the head of vector b. When we talk about changing direction of the vector, we just add a minus sign and we reverse the arrow, the direction being the same. Note that this line and this line are parallel, and this line also are parallel. And this vector here, the direction remains the same everywhere. It's just that the resultant vector changes in direction and magnitude. Now let's move on to part L. So we're gonna be looking at how to represent a vector as two perpendicular components. Now any vector can be considered as having a vertical and a horizontal component. Let's take for example this vector A. Now I'm gonna draw two axes to show the vertical and horizontal axes, which I'm gonna use to calculate the vertical and horizontal component of this vector. So here are the axes, and in order to draw the components of this vector, we're gonna say that this vector makes an angle theta, while the horizontal. And I'm gonna draw the horizontal component first, which is along this line here, and the vertical component is along the y direction. So this is your horizontal component, and this is your vertical component. Now to calculate the horizontal component, we just have to apply trigonometric ratios. So we'll take the magnitude of vector A, and by applying trigonometry we'll see that eventually the length representing this vector is going to be cos theta. So that's A cos theta. And for the vertical component, it's a sine of theta. Now a trick to remember that the horizontal component uses the cos and the vertical component uses the sine. We try to visualize it like this. So we have the vector here, and when we find the horizontal direction, we just have to close the angle. So it's like moving this part here. So we close the angle. Now the word close begins with a C, so that's cos, because cos begins with a C. So we close the angle, it becomes cos, and when we open the angle, it becomes sine. So with the component of vector, we reached the end of this video, and I hope you guys has enjoyed it. And please leave a like and a subscribe button, and any question of yours will be most welcome in the comment section. Thank you.